we go. All right, how is everyone doing today? Can you hear me in the back? Yeah, okay. All right. Does anyone have any questions before we get started? Okay, cool. So we left off looking at those chair flips. And I think it's easiest if you see it with an actual model kit. So when I say farthest left stays farthest left, and farthest right stays farthest right, what I mean is that in the physical space, they are staying in that position. So right now, this is that relative chair, where this is going that down part for here. We got our little up flap there. So these are those corner carbons. I'm taking this left carbon, bending it up. The carbon on the right gets bent down. That one up, there. So they're just shifting, doing this little wiggle in space to now be that far left, far right. They stay in that same relative location. The ones in the front stay in the front. So this carbon that I numbered 6 is this carbon. When I do this chair flip, where it's right here now, because we're on this chair, so it's number 6 right now, right here. When I do this chair flip and it goes over, it's still right here. Students think that it's rotated. It kind of looks like it's rotated, but it's still in that same relative location. It is still that front carbon. So that's why I said that it's easiest if you number them and just make sure that when you number it, you're either always going across the back or you come across the front, because that'll make sure that you're still maintaining the same carbon location. So you just want to make sure that all you're doing is this little wiggle. And when we do that wiggle, you can see right now, all of the little green ones, these are all axial, and the blue is axial. All of my white are currently equatorial. They're pointing out to the side. When I do the chair flip, now all of the ones that were axial are now equatorial. All of the equatorial went to axial. So now they're just straight up and down, right? So what is up, though, stays up when we do the shift, right? You can see that this is down axial. This is up equatorial. When we do that chair flip, now it's up axial. It always stays up. The facial selectivity stays the same. It's just this little wiggle back and forth, all right? That's all we're doing. When we do the chair flip, there are the different energies associated with it. The chair is going to go through the chair to a half chair to a twist boat to a boat. The only ones I require you to know are chair and boat, but the idea is that in order to get between the chair conformations, you have to like flatten it, bring it up. Now I'm boat. The boat is going to be higher in energy. They're clicking, they're hitting each other. So this is the boat conformation where it's this U shape. Then the other side comes down to get into the other chair, right? So it's up, down, down, and they go back and forth. All right. Actually, one other thing before we move off of When you're looking at a Newman projection of the chair, what we're doing is taking a certain perspective. We're going to be looking down two parallel bonds. So if I'm looking down these two bonds, so here's my chair, that one, so it matches the top chair. So right now, this carbon is the one that has the star, is the one that has the black and blue attachments. That's the star carbon. So I'm going to look down these two bonds of my chair. That's that perspective that I'm taking. To do the Newman projection, it's easiest if you imagine that like you have a left eye and a right eye. So the left eye is going to look down this back bond. The right eye is going to look down the front bond. So what we're doing is we are taking our chair and turning it to get this Newman projection, to see that we have these Gauss interactions where everything truly is staggered, where you get those 60 degrees between everything. And now my front carbon, this right here, is that star. So that's all we're doing is we're going from the chair and then we're imagining that we're looking down two of the bonds to get into the Newman projection. You can look down any two bonds. So we look down those back two. I could look down these two. And then I get that Newman projection. So whatever bonds you look down, you can look down any of them is what I'm trying to say. When we do our chair flip in the, how did I do it there? When we're in the Newman projection, so when I do this chair flip, I'm imagining that I'm pinching the front and the back carbon. So the front flips up, the back flips down. There we go. The front left carbon stayed front left. The front right carbon stayed front right. All that we're doing is this little wiggle. So when you're axial, so this green was axial, now it's up equatorial. When I do that chair flip again, now it is up axial, right? So all it's doing is this little wiggle. It's just shifting a little bit. So it's not actually totally changing location. It helps if you keep the carbons in the same place and then imagine what the attachments are around it. Okay. So let's draw those Newman projections. So if I'm looking at this and I'm going to look down these bonds, and actually here, we'll do the circle and the dot. So those are the relative carbons. So my left eye is going to look down the back carbon. My right eye is going to look down the front carbon. You need to imagine where those axial and equatorial positions actually are. So I'm going to start pretending my right eye is closed, and I'm just going to draw the Newman of that back carbon. So I get my circle and my dot. I see that my axial is going straight up. So that up axial is going to be that straight up on that front carbon. That is my axial position. And then I get my upside down Y. When I look at the circle on the back carbon, the axial position is straight down. So my line goes straight down. And then I get a normal shaped Y. My equatorial positions are out to the sides. So these are the equatorial positions, are out to the left for the left eye. So then the chair, the middle of the chair, are going to be to the right on that Newman projection, are going to be in the middle of the Newman projections. Cool. So then I close my left eye, and I'm going to open up my right eye. So then I, again, get my circle, a little aggressive on the circle, get my circle, my dot. On the right eye, I again see the line go straight up on the front carbon. So I go straight up on the front carbon, and then I get my upside down Y. On the back carbon, I see it goes straight down for the axial. So that goes straight down. That's where I get my methyl. And I get a normal shaped Y. So then what I'm going to do is now I'm going to open both of my eyes together, and I'm going to converge the image so that now they come into view together to see that this is my Newman projection of that chair. Remember, with the Newman projections, we are assuming line diagrams. So you have to have the spokes there, but we assume it's a carbon unless something's written. So you have to put in the hydrogens if there isn't actually a substituent there. So I'm going to move these axial and equatorial labels out to put my hydrogens in. So that is your Newman projection of your chair conformation of that particular chair. All right, so when we go to do a chair flip, you can imagine it being a chair flip from the original chair, in which case, remember, farthest left stays farthest left, farthest right stays farthest right. So the right side comes down, the left side goes up. So those are those two carbons. So my methyl is going to be attached to that carbon. That's where my methyl goes. That's what I was trying to illustrate with that actual model kit, is that it looks like this is rotated. It's not rotated. It's just shifting a little bit in space. It's going to be here. Down stays down, but axial goes to equatorial. When you're in the middle, it has to be parallel to 2 bonds away. So it has to be well, it always is parallel to 2 bonds away, but we have to be parallel to those outside bonds when you're in the middle. So that's where my methyl is located. So I'm going to keep these as the starred carbons, being those anchors on the far ends. And I'm now going to look down, well, it's actually the same bonds, those middle 2 bonds, but I'm going to look down it this way in that chair conformation, or the chair flip. So again, I'm going to do left eye, right eye. So with my left eye, get my circle, my dot. Now my axial on that front carbon is going straight down. So I get a line going straight down. And then I get my normal shaped Y. On the back carbon, the axial is straight up. So I get a line going straight up. And I fill in the hydrogens on those axial and equatorial locations. Then I close my left eye, I open my right eye. For my right eye, I see that my axial is straight down. So I get my line straight down and I get my normal shaped Y. On my back carbon, my axial is straight up. So I get the line going straight up. Bless you. My methyl is that down equatorial position. So the methyl is here. And then these are all hydrogens. I open both eyes. My chair converges. Gotta actually make the bonds meet. And what I'm seeing is that that methyl is still attached to the same carbon. It's still attached to the circle. It's also still down. It is just going from axial to equatorial. So in the chair flip, you can do it just purely in the Newman projection by making sure that you're keeping the same carbons attached and then just going from axial to equatorial. A lot of students will make the mistake of when they go between the chair flips, they'll keep that methyl here, but now it's attached to the front carbon. That is going to be a structural isomer. You change the connectivity. So you can't change the connectivity, you gotta keep it in the same place. It is connected to that circle, the back circle, and it has to stay down. But axial goes to equatorial, equatorial goes to axial. Right? Does that make sense? Okay, cool. When you're in the chair conformation, it's now easier to see that you have this Gauss interaction. So here, there is a 60 degree between two non-hydrogens. Remember, that's what makes it a Gauss interaction. It's just it's 60 degrees between two non-hydrogens. So that is a steric interaction right there between those two substituents, between the ring itself and your methyl substituent. Whereas when it's equatorial, now I don't have those Gauss substituents, it is more stable. When you are axial, there is an additional steric consideration, which is called a 1,3 diaxial interaction, which is the fact that your axial substituents are going to bump into each other as well. So I get this interaction between the two axial substituents. The 1,3 diaxial interaction does not require two non-hydrogens like the Gauss interaction does. It just requires at least one non-hydrogen. It's called a 1,3 diaxial interaction, not because of IUPAC numbering. It's just saying that if you were to number the connectivity, they're 3 carbons away from each other. That's where you're getting the two axial substituents. So that's where we're seeing that steric interaction. So the 1,3 diaxial is just talking about the position that it's in. And we are going to say that we want those large substituents to be equatorial, because when they are equatorial, it's going to be more stable. More stable, lower in energy. That is favorable, that is what we see. So you want to minimize this 1,3 diaxial interaction, so it'll do a chair flip so that the substituent can be in the equatorial position. We can also see this happening with our fused rings, where we can see that a cis-decalin is going to be less stable than our trans-decalin. So the cis-decalin is where those hydrogens are both pointing up. That's less favorable because I see that I always get one group axial, right? That's less favorable. Whereas when I'm in the transdecalin, I can now get that ring to be both equatorial. So we can also see that some fused rings are going to be harder to make, some are going to be easier to make, all because of that connectivity. Large groups want to be equatorial. That is more favorable, that is more stable. Right. Are there any questions about our rings? Cool. That finishes chapter 4. So chapter 5 is looking all at this stereochemistry concept. So we've been talking about stereochemistry a little bit. Now we're going to look at it in great detail. We're going to revisit our different isomer relationships. So that's where we're going to start. And then we're going to look at our chiral atoms. Most of chapter 5 is going to look at our optical isomers. That's where we're going to spend most of chapter 5. So that is our chiral atoms. We're going to spend a lot of time talking about R and S assignments, which are going to be absolute stereochemistry. And then we're going to look at chirality at the molecule level. We're going to have chirality at 3 levels: the atom level, the molecule level, and the mixture level. And we're going to talk about how we build up from the atom to the molecule to the mixture, and how that impacts our chirality, and at what points you can lose chirality. So we're going to talk about it in that order. But first, why does stereochemistry matter? The reason that it matters is because our bodies in nature have handedness. So you have a right hand and a left hand. Right hand and a left hand. So if you were to go to the person next to you and you both shake with your right hands, that's normal, right? Like if you're trying to shake someone's hand, our convention is you stick out your right hand, right? So like go ahead and do that if you're cool with it. Like shake the person next to you with the right hand. That works, right? Now one of you switch it to be your left hand. So one of you do right hand, one of you do left hand. That's weird, right? Like that doesn't work. It doesn't fit. Now both of you do your left hands. That works. It might not feel as normal because, you know, our social convention, but like it works, right? That's because your body is chiral. You have handedness. There actually is a difference between your right hand and your left hand. So our molecules have the same thing. They're going to have that same handedness. So your tongue is going to have receptors. It's going to have one hand. So you're going to have a little hand hanging out on your tongue. And a molecule comes along, and if that molecule fits, and it is the correct hand, and they can shake hands, you taste one thing. And then when you get the left hand hanging out on your tongue, and then the other molecule comes along, and that fits and it shakes, you taste something else. The molecules can look so stinking similar, where the only difference is left hand versus right hand. And that is the whole difference between a spruce tree and an orange. Like those are two very different scents. And I don't know who's licking a spruce tree, but like they're very different smells. Your nose has the same thing. They're all different receptors. So your body can tell the handedness of a molecule without you even having to be conscious of it. Nature is that selective. It's part of how we get so much diversity and why carbon is so special, is because it can also be chiral. So not only is the connectivity important, but the three-dimensional arrangement is going to immediately control how you perceive the world. There's also a very significant drug relevance. So thalidomide in 1957 was this miracle cure for pregnant women, where it was this wonderful cure of morning sickness, and it was really effective. The problem is only one of the handednesses were useful. Only having that clockwise orientation was what treated morning sickness. The problem is it was sold as a racemic mixture. It was sold as both the left and the right hand. It was sold with the counterclockwise arrangement. That caused birth defects. So women were getting this initial relief, and then it was damaging their fetus. So having the handedness is really important because this was totally safe and had great therapeutic responses. This one was injuring and killing babies. Like there was big differences in the handedness. Your molecule or your bodies can tell that in the molecules. We can also have spearmint versus caraway. We can get the same thing where they look very, very similar, but they're what are going to be called enantiomers because they're non-superimposable mirror images. So if I imagine there's a mirror here, this left side and the right side, those two molecules, they're the mirror images of each other. But if I take that spearmint and I flip it over like a pancake so that they are now exactly on top of each other in every way, what I see is that one is a wedge and one is a dash. The dash is the spearmint. The wedge is caraway, like the rye bread, like two very different flavors. That's why we care about chirality, because we have this handedness and nature uses that to tell the difference between the different molecules, to get this extra level of diversity and to know it. The thing I find really interesting is sometimes it's just that simple of like different flavor profiles, but a lot of times, especially with pharmaceuticals, it is more likely this, where usually one is really helpful and the other one like kills you, which I just find fascinating that like that's how the body is set up, where it's like, hey, I can only accept this handedness, like I can only take the left hand, you put the right hand in here, and we're gonna have problems. Like, I just find that fascinating, that the body is like, one heals, one destroys. It's not always that way, but it seems like a lot of pharmaceuticals have that, where the chirality matters. All right, so let's put ourselves on the map. Let's try to figure out where we are with our stereoisomers. So isomers are going to be where you have the same molecular formula, but different arrangement. Right? That makes you an isomer. It's just that you are the same molecular formula, you have the same number and type of elements, but we're going to have a different arrangement. The constitutional isomers are going to be the ones that have the different connectivity. Within the constitutional isomers, we get three subsets. I don't care if you actually know the three subsets. Usually skeletal is used interchangeably with constitutional. These are also sometimes called structural isomers. They're all synonyms. But we get our three different options. So if I'm looking at, this is my original molecule, how would I name this molecule? So it's butanol, but what kind of butanol? Okay, location, we need a number. We gotta say where the alcohol is located. So it's 1-butanol or butan-1-ol. If I go from having the oxygen on the end to oxygen in the middle, that is a functional isomer because I'm changing my functional group. What functional group is this? Yeah, the ether, yeah. How would you name that? So remember, our ethers are only ever substituents. You use the root of the shorter side with oxy to say that this is a methoxy group, and then you list the backbone. So then it's just propane. So that is methoxypropane. Did anyone get that right? No? Okay. That's all right. Your exam is, when is your exam? Like a week and a half? Yeah, that sounds right. Yeah, you have a week and a half to get good at that. You're good. All right. Then we get skeletal. Skeletal is talking about a different backbone. So my skeletal is saying that my alcohol stayed in the same place, but I took a piece of my carbon backbone and I moved it over. So how would I name that? It's not going to be isopropyl alcohol, but I appreciate that you're recognizing it's a 3-carbon backbone. So we get prop for our actual root, and because all single bonds between them, our alcohol is still going to be on carbon 1. So it's still propan 1-all. What do I do to account for that 1 carbon substituent? 2-methyl. So this is 2-methyl propan 1-all. Positional is just where you move your location of your functional group. So how would you name that molecule? 2-butanol or butan 2-ol? So the thing to recognize with these is that they're going to have different IUPAC names. So if you are naming it differently, then you are a constitutional isomer, because that means your connectivity is different. So you get a different IUPAC name. Your stereoisomers are going to be where you have the same connectivity, but a different 3-dimensional structure. So you're just going to differ in 3D. Our conformational isomers are that subset of the stereoisomer where all we're doing is rotating that sigma bond. It is the exact same molecule, we just rotated it. So conformational is kind of a weird one because it's literally the exact same molecule. It is just drawn in a slightly different way. All I did was rotate that sigma bond. It's important to note that it's not flipping the molecule over. That is not conformational. That's just taking a different perspective of the same molecule. It actually has to have the different energies with it. So it's actually a rotation of a bond. That makes it conformational. Configurational is where you can't rotate the bond and get the same molecule back. So you can't get the same molecule just by rotating a bond. So we're going to have these kind of either a locked conformation or a different 3-dimensional assignment. So geometric is where you have the restricted rotation. Geometric is our cis and trans, or the E and Z. So remember that for trans Trans means opposite. And if you're using it for the alkene, for the double bond, you have to have just the 1,2 disubstituted. You need one and exactly one hydrogen on each side of the double bond in order to be able to use cis and trans. Trans being opposite, cis meaning same. Our rings also got that same cis and trans, but they were talking about the facial selectivity. So trans would be where you have a wedge and a dash, whereas cis is where you get 2 wedges or 2 dashes. They're on the same side or opposite sides. E was the same thing as trans, but we used E when we were more than 1,2 disubstituted. So if you had 3 or 4 non-hydrogens on your alkene, then you could use E and Z. E was that high priority are on opposite sides. Z is where the high priority are on the same sides of the double bond. Right. All of that should be a review. We've done all of that so far. So the new part is this last corner, our optical isomers. Optical isomers are going to rotate plane polarized light. That's going to give us an optical isomer. We're going to have relationships between our optical isomers where they can be either diastereomers or enantiomers if we are optical isomers. So your enantiomer is defined as a non-superimposable mirror image. So that's like your left and your right hand, where when they are mirror images, so they're facing each other, they can't, if I set it to actually be so they're actually facing the same way and slide them on top, or sorry, don't face them the same way. So they're just, these are mirror images and I slide them over, they're not exactly the same. So they're non-superimposable when they just slide over. So they're mirror images, face them forward, slide them over, non-superimposable mirror images. Those are going to be your enantiomers. I personally don't like that definition. I find it really confusing and I don't know, like it never actually worked in my brain, as you can probably tell from the fact that I did it wrong on my first demonstration. So what I find easiest is to think about it as we're going to flip 100% of our chiral centers. Every wedge goes to a dash, every dash goes to a wedge. 100% of them get inverted. So that's what we're seeing, is that if this is my original molecule, every wedge goes to a dash. That makes it the enantiomer, is that I'm inverting every single chiral center. Every wedge goes to a dash, every dash goes to a wedge. That is my enantiomer. You will only ever have one of them. Because there's only one way to flip everything. Like if you're inverting everything, you only can do it one way. Diastereomers are the non-mirror images. Which I also think is a terrible definition. So the diastereomers are going to be where you invert some, but not all. So greater than or equal to n-1. So you invert some, but not all of your enantiomers, or sorry, of your chiral centers. So here, my bromine went from a wedge to a dash, and then the fluorine stayed a wedge. So these are going to be diastereomers. I flipped some, but not all. These are going to be diastereomers because now bromine stayed the same, but fluorine went from the wedge to the dash. I flipped some, but not all. If you flip all of them, you are an enantiomer. You flip some of them, diastereomer. In order to have a diastereomer, you need at least 2 chiral centers. So N is going to be greater than or equal to 2. Because if you only have one wedge and you flip it, you've now flipped 100% of your wedges. So you are now an enantiomer. So if you only have, like if this side doesn't exist, then, and I'm looking, like I'm ignoring that fluorine bit, you can see that when I flip that one wedge to a dash, that was 100% of them. That makes it an enantiomer. So if you only have one and you flip it, you're an enantiomer. So you need at least 2 to be a diastereomer, so you can flip some but not all. So this is where we're going to spend the next week focused on, is all of the nuances of this corner of our stereoisomers. Okay. So our chirality exists at 3 levels. We have chirality at the atom level, the molecule level, and the mixture level. You usually need a chirality at a lower level to get at the higher level, meaning that we're going to build up. So you're going to start here and build up, so that if you ever lose chirality at one point, then you lose chirality at all remaining points. Usually, there are a couple of exceptions. But in general, we're going to do it in that order. So to figure out if you have a chiral mixture, you ask yourself, do I have chiral atoms? Then you ask, do I have a chiral molecule? And then you can ask, do I have a chiral mixture? Right? You have to do it in that order. Find the atom, then the molecule, then the mixture. A chiral atom is going to be an atom that has 4 different substituents. It must be sp3 hybridized. It must. That's a part of the definition of being a chiral atom. We're going to mark it with an asterisk to indicate that it is a chiral atom. The most common atoms that exhibit chirality are carbon, phosphorus, and sulfur. What's actually kind of really interesting is right now, a lot of research is going into finding chiral phosphorus compounds and figuring out how to make them easily, because that's where a lot of pharmaceutical chemistry is headed right now, is trying to find chiral phosphorus groups in order to have that easy adding on of phosphorus and then getting that handedness that's needed. So increasing the selectivity by easily just putting on a handedness at the end. So that's where a lot of the research is going right now, which is really, I find really interesting. But anyway, so carbon and sulfur are pretty well studied. Carbon is where we're going to spend most of our time. One group can't be a lone pair of electrons. So nitrogen is not going to be able to have that chirality because it has the lone pair. If you make it really, really cold, then you theoretically can exhibit some chirality, because now all of a sudden you're starting to restrict the movement of the molecule, and now you can get the 4 regions to start to have chirality. But in general, when we're looking at room temperature, or like any normal temperature, like even down to minus 78, you're not going to be able to have a group be a lone pair of electrons and actually be able to observe any sort of chirality. So we're going to say you need 4 different substituents, and you need actual 4 different substituents in order to be a chiral atom. There are a lot of synonyms to the term chiral atom. It can also be called a chiral center. It could also be called a stereocenter. It could also be a stereogenic center or an asymmetric center. Technically, these words are different. There is some nuance to it. We won't get into that. In this class, I'm only going to give you examples where all of these words are interchangeable. So anytime you see any of these words, they're all saying the same thing. That this is that N value that we were just talking about. That is the just chiral atom, chiral center, stereogenic center, asymmetric center. It just means carbon with 4 different things on it. That's what we're getting at. So if we look at this first example right here. Right. To find our chiral atoms, you need to find the different groups that are attached to it. You can use wedges and dashes as a guide to help you find your chiral atoms. But when in doubt, you can go through all of them. So I know that that is not going to be a chiral carbon because it has 3 hydrogens on it, and hydrogens are then the same. I need 4 different things. That carbon has a methyl group to the left, a bromine on the wedge, a hydrogen on the dash, and the right side of the molecule to the right. Those are 4 different things. That is going to be a chiral center. My CH2 is not a chiral center because it has 2 hydrogens. Those are not 4 different things then. So that is not a chiral center. The carbon over here, that gets our left side of the molecule, which is unique. The hydrogen, the alcohol, and a methyl, those are 4 different groups. That is also going to be a chiral center. And then that CH3, again, cannot be a chiral center because it has 3 hydrogens. That's not 4 different things. So in this molecule, we have 2 chiral atoms. All right, go ahead and try the next one. Try to find how many chiral atoms you have. Actually, do all 3 of them. All right, so for this one down here, how many chiral atoms do you have? 1. There's 1 chiral atom. So when I go through these, CH2s are no, 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 double bond, no, because it has to be tetrahedral. It has to be sp3 hybridized, so it can't be the double bond, and it can't be that methyl. So then the only one I have to inspect is here. I see that I have the amine, the hydrogen, the left side and the right side, and the left side and the right side are not equal to each other. So that is a chiral atom. That is the 1 chiral atom. Right. Let's go to the upper right-hand corner. How many chiral atoms are there? 0, good. So again, go through CH2, no, CH2, 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 CH2. All right, I just have this one to inspect. I have the mean, the hydrogen, and then the left and the right side of the molecules are exactly the same. I have symmetry. If there is that symmetry, if it is exactly the same, then you have no chiral atoms. It is an achiral carbon. Meaning not chiral. All right, how about this last one in the lower right? Zero. Another 0 chiral atoms. So when we look at this, all right, we see the CH3, CH3, CH2, CH2, CH3. Okay, so we can get rid of all those. So now we're just inspecting this one site. When I look at it, my 4 groups are that methyl, a methyl, hydrogen, and a propyl. These are the same. Be careful, watch out for when certain ones get labeled for emphasis. They're still both methyl groups. They are the same thing. There are 0 chiral atoms in this molecule. So with that, I give the warning of just because you have a wedge or a dash does not mean you are a chiral center. We just had 2 examples here where we had wedges and dashes drawn in, but it was not a chiral center. Likewise, lack of a dash or wedge also does not mean that it is achiral. So for example, how many chiral atoms are there in this molecule? It is not 0. More than 2. Three. So we again can cross out all of our CH2s, that CH3, so that now we're like, all right, cool, these are the only 3 that I need to inspect. So when I look at this one on the left, I see that I have a left side of a ring, a methyl, a hydrogen that's implicit, and then the right side of the ring, and those are not equal, so that is a chiral carbon. All right, then I inspect this one. I see that there's the top part of the ring, a hydrogen, the bottom part of the ring, and that chain on the right. Those are 4 different things. That is also a chiral carbon. That's usually the one that most students miss. And then for this one, I see the alcohol, the hydrogen, the methyl, and then the whole left side of the structure. That is also a chiral carbon. So there are 3 chiral atoms in here. Having a wedge and a dash does not mean it is chiral. Lacking a wedge and a dash does not mean that it's achiral, not chiral. You always need to check to see if you have 4 different attachments to that carbon. All right, have a wonderful weekend, and I'll see you on Monday.